Okay, so the recording has been started. Um, okay. Okay. So I hope my screen is not visible yet, right? So let me share my screen. Uh, I hope my screen is visible. Okay. So let's start. So welcome to the week 5 of the course. Right. So yeah. So what we will do today is actually give a quick revision on what we have done so far, and then move towards a new class of algorithms um, that we will be covering. Let's say the model tree methods, right? So if you have attended all the classes till now, you can solve grid worlds, right? You can solve grid world environments, fairly large grid world environments with policy improvement, right? So yeah, so let's just quickly go over all the theoretical details and all the algorithmic details, and then we'll move towards a new class of algorithm where we do not have access to the transition dynamics or the reward dynamics. We can only interact in an environment, which is a more realistic view of the RL problem, right? So that we don't know anything about the environment. We can only interact in the environment. Okay. So yeah. So this is the I'm just breaking this slide up in every week because if some new participant is joining, then he must know that this is the Python manager we are using for implementing the algorithms, and you can obviously check out the Python prerequisite, like not prerequisite, I guess it's a helping course in this. Uh, you can also go and check it out. Now, this is the entire thing that we covered, right? Last like for the last few weeks. Um, yeah, and this was the last week. So what we covered till now is different world definitions like MP, MRP, MDP, right? Then the class of algorithms like classical RL, deep RL, and all those things. These are like theoretical concepts, right? And then we covered some theoretical concepts like return, what is a discount factor, um, and all those things, right? And finally, we can solve MDPs in two ways. Assuming that we can evaluate a policy, we can look through all possible policies and like rank the policies based on the value, right? Another way is improve the policy with the value and basically solve it, right? So we'll just quickly go over all the algorithms quickly. Okay, so this is the RL loop. This is the Markov assumption, right? And this would like really click in your mind. So till now, we have been discussing this for a good amount of time. So I know that these RL concepts need some time to actually stay in your mind. So that's why we are revising it in every week. So this is the Markov assumption, and these are the different world models. And this is, let's say, the Markov process, right? When we have only the transition matrix, no reward or nothing. Finally, in the reward process, we have reward and discount factor. So two new concepts arise from here. Is one is this return. Return is discounted total sum of rewards from a state, and value function. Value function is basically expected return from a state, right? Uh, Now in Markov decision processes, the policy and state action value function comes, right? The policy is basically your state to action mappings. It can be deterministic, it can be probabilistic, right? And state action queue function, we have seen last week, right? It's like a value function where you take an action A1, right? And then follow the policy pi, how much expected reward you get, that's known as its value function, like state action value function, right? Okay. And this was the policy evaluation algorithm, first algorithm where we have exact solution, right? Exact solution is like V is equal to R plus gamma PV, which comes from the Markov unroll. So the Markov chain, right? It's like a recursive chain. So we can do something like this and just inverting the I minus gamma p and multiplying it with r would directly give us a solution for V, right? But we have a problem in this. This matrix might not be invertible. So we also learned the iterative method that until my value converges, I can just do an iteration over a, let's say, initialize all value with 0 and then do an iteration. And this will eventually converge with the same exact solution, right? Now I can solve an MDP by just adding all policies that can be possible in that MDP and converting it to a corresponding MRP. And this is how you can convert an MDP to an MRP, right? From RSA, if you mention pi, that gives you RS, which is an MRP. And from PSAS, if you just mention pi, it gives you PSS, right? So then what we can do, we can basically get the value function for that MDP, sort all the policies based on the value function. And that's what we did, right? That's what we did. And we can kind of evaluate the value function for all possible policies. But the problem was this computation in this algorithm grows exponentially, right? So let's say solving this 9-state environment is taking like 36 seconds or so. But whenever you go for a three more state environment, like 12-state environment, it takes 32 minutes, right? And this was the logic that initially it took 36 seconds because there are three more states and each state have four choices, up, down, left, right. It's a computation, it is like four times larger, right? If we go and see, like check the number of policies, it's that much time larger. So because of this exponential growth, you cannot solve larger environments, right? So there comes the policy iteration or policy improvement algorithm, where you start with the initial value and policy. Now, see, this is the dynamic programming loop, right? Or this is the iteration. And then you improve the policy over the queue and then improve the value over that queue, right? Until this converge, if you go, what it what it guarantees is a monotonic improvement, right? So you are not, so if you just go previously, these are all policies which are not improving over the last one, right? So this is the best policy in this entire in the entire scene, right? So what we are doing here, we are not actually like brute forcing all the policies. Rather, we are only looking into whatever is the next best policy, right? We're always improving the policy, so or improving the value function. So in that case, we can converge really quickly, so within few seconds. So see here, for a much bigger environment, which like more than uh, take- so the number of policies that are possible for this environment, this large of an environment, is more than the number of atoms in universe. But still, we can solve it uh, within 140 or 142 iterations, right? So that was a very powerful algorithm from our perspective, right? And it can solve it within like is not in hours, it's solve it within seconds. So that was the end of model based reinforcement. So by model based, what we mean? We know the P and we know the R, the probability transition dynamics and the reward dynamics. Then it counts as a model based algorithm. Okay. And now this is the classification of RL algorithms. Okay. So irrespective of whether it's classical reinforcement or deep reinforcement, these are the different type of algorithms we have based on how much knowledge we have about the agent and the environment. So model means the environment, P and V, sorry, P and R. Okay. So if I know the model and the value and the policy, which is the case in the previous cases, right? So that becomes my model based reinforcement, this block. Now, if I only know the value, not the policy, that becomes my value based methods. And if I only know the policy, not the value, that becomes my policy based methods. And now if I do not know the environment, I know the value and the policy, right? That becomes my model free methods. So that's what we are trying to do now. We have the value, we have the policy, but we can only interact in the environment, cannot get the P and R matrices. Okay, and there is another class called actor critic methods. Um, that in that case also you basically have value function, policy function as and some knowledge of model. Okay. Okay, so we'll explore all of them later on, but for now, you know what is model, you know what is policy at least. Value function means your state action value function or normal value function. Okay, now we'll see what is the model free method. Okay, okay. So how you can interact in an environment. So this is the loop for interacting in an environment for the grid world package in any other package too. So if you consider any other open source package, the, this is the structure you want to interact with. Okay, it's the same structure. So we actually kept the same structure here also, so that whenever you move to a new environment, let's say OpenAI, Gym, or any other, it doesn't your code doesn't need to be changed. Okay. So you can define a grid world, right? And for let's say I want to interact for 100 episodes. So what do I mean by episode? There is a concept of an episode now. Earlier, because we are not interacting, we didn't have any concept of an episode, right? So episode means starting of an interaction session to ending or ending of an interaction session. Okay. So ending can be of two types. One is your agent is lost and you want to cut off the interaction. Okay. That's your interaction. Let's say the agent has lost in that environment. So you don't want to keep exploring, right? You want to just cut off the agent, right? So that means the agent might have a lifetime. Okay. And your agent can also reach a terminal state or a goal state. So these three ways are in an episode may end. So this max episode steps. So this is the life of the agent. So how many maximum steps it can take? So 1,000 means it can at max takes 1,000 steps in that environment. Okay, to solve it. If it doesn't solve it um, or if the environment doesn't naturally end within 1,000 steps, it will cut off the agent or just say okay the environment ended. Okay. So for 100 such trajectories, what you do, you first reset, right? Reset means newborn agent. Okay, so environmental reset gives you a current state which is of a newborn agent. It can be of the starting state of the environment in a grid world, right? Done variable, this is very important. Done variable means we are not done yet in the environment. Okay, so done is false initially. While not done, while environment is not done or environment is not ended, right? Environment not render, this is an optional thing. So if you render it, it will basically show up in a graphical window, right, where it's taking the action. Also, then you take action equal to any random action. So here you are basically putting the policy. So for this example code, we are showing that it's a random action, right? But you can anyway select a policy, like you are just replace this call with a policy which will give you action. Okay. Now this environment.step, it takes in action. Okay. And what it will take you to, it will take you to a next state. It will give you a reward and a done variable. Done variable means whether the environment ended or not. You reach the time limit or you fall into a trap state or you basically reach the goal state. Right. So in all those scenarios, done will be true. Okay, and info is something like it gives you reasons why the environment end. If the goal state is reached, it will say goal state reached. If it fall into a, let's say, a whole state, right? Then it will say okay, the agent fall into a whole state and the environment ended. So that type of like why the environment end, that information gets stored in the info variable. Now, see, this is the interaction, right? So current state, you take some action, you get some reward, you get to the next state. Now in the next iteration, your current state will be the next state, right? Now you basically need to replace the current state with the next state. And this timer.sleep is just to, you can visualize the all. And then at the end, after this runs for 1,000 such episodes, right? It then gives you this environment.close. So basically you close out of the environment after you run for such 100 trajectories, and every reset it start from the same initial state. Okay. And then at the end you just close out of the environment, so your rendering stops. Okay. And this is an example of how it prints. So okay, so this is an example of how it prints, basically. Right. So SAR, SA, these are the trace transitions, and each state is basically uniquely identified with a state ID. So yeah, for the grid world package, every state is like 0, 1, 2, all those things, right? Okay. Now, so we'll see how it works. So let's open up the this week's thing. No, so we'll take the big environment only, right? Let's just take the big environment. Just copy it. Model free interaction. So model free means we don't have access to the PNR. Assuming, so we actually have access to them because we are using the package, but yeah, assume that we don't have access. Okay, run, and then I can just copy paste this code, right? Oh, environment is already defined, so let's not put it here. If I run this, this should actually render the environment for me and give, oh, what happened? Time is not important. And also, this is like a too big of an environment, right? So let's just not have that big of an environment. Set this one. Time. Okay. Now if I run, see, this is what is happening. It's just taking random actions. Okay. And you'll see when it closes out, after 1,000 step, it will get reset. Still taking 1,000 steps. So let's not do 1,000 steps. Let's give it less time to explore. Okay. So maximum steps, let's say make it 10, which is impractical for this environment, but let's explore it for 10 steps for each trajectory. Okay. And here we print on trajectory I. Okay. So if I run this, then run this, so this is what is happening. It's okay, reset. Then again, reset, reset. See, always it's just goes for some time and then get resetted, right? It's trajectory 8, trajectory 10. So such that we will have 100 such trajectories. You see, whenever it goes a bit away from the initial state, it reach the 10 step limit and then get resetted to the initial state. Again, these are the trajectories. Okay, so let's stop it for now. Get the idea. And let's inspect a trajectory. So it start with 0, take action 3, reach to get a reward of -1, reach to 0. That means action 3 is something like left or something, right? It hits the wall and just move to the 0. Then again it takes action 3 and reach to the same state. Then take action 2, reach to the same state. Take action 1, it reach to the 10th state, right? So this is how the environment progresses. And we have limited to 10, like 10 steps per episode. So it will be only 10 steps, right? Unless it is so small that within 10 steps it's reachable, the goal state is reachable, then it might have less number of states in the trajectory. Okay. Okay. Now, these are the classification of model free algorithms. Okay. So let's see. So what do I mean by model free? Model free means you don't have access to the probability transition dynamics or the reward dynamics. You can only interact in the world, right? Now, it can have two type of algorithms. One is evaluation and then is control. What is evaluation? It's similar to finding out value. So in the model based also, we have two type of algorithms, right? One is how to evaluate a policy, and this next one is how to get a policy from a value, right? That becomes a control algorithm. So whenever you are trying to evaluate a policy, that's known as an evaluation algorithm. So model free evaluation, let's say I know the policy, I know how I like model free doesn't say that you don't have access to the state space or the action space. You have access to the state space and the action space. Now I can come up with a policy like as a state to action mapping, right? So given that policy, what is the value I am getting? That's an evaluation algorithm. Okay. Now control means different thing. Control means how I can come up with a better policy, just like the policy tradition in your the policy improvement in the model wasting. We can come up with a improved policy from the this q equal to r plus gamma pv iteration, right? Take the argmax of q, that will be my improved policy. Similarly, we'll see how to control in an interaction or a model free scenario later on. First, we need to see how you can evaluate a policy, because the algorithm control algorithms take ideas from the evaluation, just like the model based thing, right? We know how to get the value from a policy, then we know, okay, now I can improve it. If I have the q value, I can improve it, improve the policy, right? So that was the logic, that if I know how to evaluate a policy, I can just improve the value, or improve the policy based on the previous value. That was the control algorithm. Here also, we'll see how to evaluate a policy, and then next we'll see how to improve the policy from an evaluated value. Okay. So the main criteria, like main classification is like this. Your model tree evaluation have Monte Carlo offline policy evaluation, Monte Carlo online policy evaluation, and then temporal difference learning or TD learning. Okay. And the control part, we have Monte Carlo offline, Monte Carlo online, same two algorithms, only now we can improve on the policy. So we have an initial policy, we evaluate the policy, we can improve the policy and then evaluate it again. Something like this. Okay. Okay. And that still it still have that algorithm that if I can evaluate a policy, I can have all possible policies and then evaluate it one by one, sort it out, and then get the best policy. But that is not very efficient that we see, right? It's very computationally expensive. So we'll not go in that direction for now. So we just evaluate and then go to control directly. Okay? You assume that if we can evaluate a policy, we can just evaluate it for all possible policies and get the best one. That is always possible. It's a brute force approach actually. Now in control, we have offline, online, SARSA, or SARSA is actually the control algorithm for TT learning. Okay. And then we have Q learning. And these are all tabular at this point. So we still have finite state space, finite action space. Okay, but we don't know the transitions or the reward matrices. We can only get access to the transition or the reward matrix, like reward, by interacting in the world. Okay. Okay, so this is what we are trying to cover now. Okay, only the evaluation part, policy evaluation with interaction. Um, so Monte Carlo policy evaluation offline, it has two type of algorithms. Every visit and first visit will say, and then online same. Every visit, first visit, temporal differential learning or TD learning, and then initially will kind of, if possible, today will also explore this how to get a policy from a value function. If we can clear that part out, then controls become really easy. Okay. Okay. So now, what is Monte Carlo policy evaluation? Is basically you take samples from the environment, and then from the samples you try to evaluate the policy. It's very, very easy. So once I just wrote it down, it will be like very easy for you. Okay, my graphics pad is connected. Um, okay, so let me open up the Canva. Okay, so we are exploring Monte Carlo offline. Offline means you see in the slides only. So weight, this is not width, okay? This is weight. Weight. We just update it. Weight. Weight. So what it says is you wait until the entire data collection. Let's say we don't have access to have access to PNR, right? But we know a policy because we are trying to evaluate a policy pie, right? So we collect data with that policy for a good amount of time, then estimate the value function. Estimating value functions mean just basically for every state you get a return, right? You get a return, you uh, take an average of all the returns. That's your value function. Okay. Um, and for online, you just wait for one trajectory, and there is a small uh, like trick from offline to online. There's a small trick how you can kind of take a moving average of the value that I'll show. First, let's see offline. Offline means you just collect data for a huge amount of time with some given policy. So, oh, sorry. Oh, Monte Carlo offline. So, given pi, right? Given policy pi, I want to evaluate the v pi, right? That's my objective. So, objective is v pi. So, what I do, collect data for, let's say, m trajectories. M can be a very large number, right? That data gets updated to D. right? So in that D, what you have, you basically have state to return pairs, STGT pairs, all STGT pairs. Okay. So basically you search that like STGT for all trajectory T, let's say capital, let's say tau, right? Let's say for all trajectory tau in M trajectories, that's your D. That's a huge data, right? It's basically an STGT pairs. Now, what you can do, you can basically take all the count of, so total G of ST is equal to total G of ST plus GT, and count of ST is equal to count of ST plus 1. Basically, you are summing of all the returns that you observe from ST and how many times you observe ST. And after, for like until while, do this for the data set D, right? For all the entries in the data, you just do this. And finally, value becomes your value of ST becomes your total GST divided by count ST for every state, basically, right? I'm just writing it for one state, but you can assume it for every state. So what is the steps? Given a pi, our objective is to collect V pi. So you collect a lot of data, right? Let's say M trajectories by interacting in the environment with that policy pi, right? Trajectory, let's say with pi, and then you just get the total sum of return from every state, how many times that state occurred, and then just divide it with the with each other so that you get the value. So basically what you get, average return from every state. Okay. Now what is first visit and every visit? So in a trajectory, see here while collecting data, right? In a trajectory, you can observe a particular state multiple times. So there are two approaches. Either you consider it every time, that's an every visit approach, or you consider it for only once. So let's just expand this trajectory. It can be like this, right? S0, then you take some action with policy, then you get R0, you take action, some like you reach to, let's say, S0 again, then you reach to you get some action, you get take R1, then you reach to S2, dot dot dot, right? Now you can take this S0 both like two times, or you just take for the first visit, right? Whenever you visit the state first. So either you can have two entries, S0 G1 or S0 G2, right? Or you can only have S0 G1 and skip S0 G2. So if we have only the first entry, that's called a first visit algorithm. If you have both the entries, that's called an every visit. Every visit. So the logic is every visit is more sample efficient, but it might have bias. That's the logic. So every visit gives you more data to, and as you increase the number of samples, your average becomes more stable, right? So it's actually more data efficient. We are not losing any data, but it introduces some bias. Every visit introduces a bias. First visit is an unbiased estimate of value. Okay. So what do I mean by bias? So let's say let's say let's say this is my original value function. Okay. Original value. But so if I go with an every visit algorithm, it might land as somewhere here or somewhere here. Okay. Whereas if I go with a first visit algorithm, it might be off somewhere, it might be on something like this. So it will oscillate within the original value function boundary, but the it will not be a bias estimate. So this extra bias would not be there. This is the extra bias for every visit. It can be positive or negative bias, but it will not be there. Okay, but that's not an issue. We can still it will be biased for every state, right? So we can still compare which state is good or which state is bad from every visit and first visit. So let's implement it quickly. Okay. Okay. So you get the algorithm, right? Do you have any confusion?
Sir,
I can
when we
please.
say in a single trajectory, same state is being visited two times. That
Hmm.
is what we mean. And
Yes.
same state can have two different kind of rewards.
Return. Hmm.
Okay, and but generally, what you have to do is you have to collect all. Let's say S0 is repeated twice in a trajectory. We will take the value g of t for S0,
Hmm.
and then two times you will have different values. We will divide that by two.
Yes.
Uh,
So we'll
that is
do this thing for
every
m
visit.
trajectories. Yeah, we'll do it for the huge number of trajectories. Not only one, but we'll collect the data for like for let's say 1,000 such trajectories and then do the averaging at the end.
Got it, sir.
Okay.
Now the difference between every visit and first visit is like first visit, first time when we go to S0, what was the G of T that I got?
Hmm. Hmm.
That is the only difference,
Yes,
right?
exactly. We only take the first visit entry for a trajectory, or we take every visit of the state. That's the difference. And in terms of what happens in terms of the value is every visit a little bit more biased than first visit. Okay, first visit is an unbiased estimate of original value.
Okay.
Okay.
Ideally, we don't expect to go to the same state on a normal behavior.
We can, right? We can. So if there is a loop in the environment and we are still explicit, so in a normal behavior means it's based on the policy. If my policy is suboptimal, right? Then I can just kind of loop in that in like let's say I am in a maze and I am not following an optimal policy. I can that's the beauty of a maze, right? I can just come into a same state multiple times if I am not able to solve the environment. So in an optimal case, we should not see same states multiple times. But in a suboptimal state, let's say any given pi, right? We might see a state multiple times.
Okay.
Right? Okay. So let's implement it. It will be very quick. So we'll go here. Uh, let's not have this big of an environment. Let's have a small environment for now. Okay, and we'll keep this steps to be 1,000 again. Uh, and let's collect data for 1,000 only. Okay, so we will write a function that will help us collect this data, this D. Okay, so these are all trajectories. These are all trajectories, trajectory 1, trajectory 2 for all the 100 trajectories. Now, what we need to do, we need to have this S and GT returns, right? Return pairs in a set or somewhere in our data, so that later on we can just loop with that entire data set and get the average, right? So what we will do, how many state we have? Uh, environment dot state count. It's 12 states, right? So we'll initialize two things. Is equal to np dot zeros state count and np dot zeros same state count done. Okay, so now these two are basically your v is your value function and n is your how many number of time each state is visited. Okay, now for 100 such episodes, you reset, you do turn is equal to false. Let's not render it for now. You take some action from a policy pi. Let's write a random policy. So let's have a policy pi to be uh, np dot random dot rand int of 0 to 0 1 to 3, right, 0 to 4, with size is equal to environment dot state count. This is the pi. Let's say we have a random policy pi, and this is my pi. And if I can show the policy, right, environment dot show pi, and this is my pi. Okay, and you see here I can stuck to a same state, right, multiple times. And now how we can go out to this initial policy is itself wrong, right? It will directly bump into the wall for most of the time. So how we can expect this will not stuck in 0? So there is a sleep parameter in the environment. See, there is a sleep. Sleep means with 20% probability, it will not do what it's supposed to do. Okay, so it's like a sleep in the environment. So even though the policy is suboptimal for the first state, it will not get stuck there. With some low probability, it will go out of that state. Okay. Okay, so sleep is important. Now we know the policy. So we get policy, we can just do pi current state, right? That gives me the current state action for that policy. And this is your agent the policy becomes your agent, right? With that, you interact in the environment, get the next state and everything. So if I just run it for some time, let's say run it for 10 steps, we'll see how it, yes, this is how it goes, right? Oh, sorry. For trajectory 0, it mostly stuck to state 0, but sometimes after it goes to state 1, state 2, state 5 also. Then after 100 or 1000 or 100 interactions, yes, it reached to it reached to the goal state with some interaction, I guess. Not 1000 interaction, within a few hundred interaction with some random policy also, it reached to the goal state. Okay, why? Because it has the sleep. With some probability, it will not take the policy, right? It will sleep. The environment has some stochasticity within it. Okay, in trajectory 2 also, it was something like this. Now, these are all fine. But we need a way to estimate GT return, right? So let's save the trajectory. So we can save the trajectory uh, like this. From collections, import named tuple. Okay. Now transaction. So transaction means this because your SAR S prime pair. Okay. Transactions is equal to named tuple. And now here you want to pass what are the different things you want to track, right? S, A, R, S prime, and GT, G. Okay, that I want to track. Now, if I run this, So did he, oh, sorry, transaction, and then I need to do this. Okay. Transaction type and this. So now what is this transaction? This is a name tuple. I can have a transaction like this: 1, 2, 3, 4, 5, and that's a transaction. You see, there is a data structure we'll be using. So transaction is a data structure that tracks all the all these things. Okay. Now we'll track each trajectory. TRAJ trajectory is equal to add empty list, and after each transaction, after printing it out, we want to track it in the trajectory. Trajectory dot append transaction, and same thing. This current state, we'll just copy it out. And see, if I don't pass something, right? If I don't pass something, it's saying this is missing an argument, right? So even though I don't want to pass something, I can put it as 0. That would be initialized to 0. Okay. So current state, action, reward, next state. Yes, right. So this is how I can store the these things. And let's put, because we don't have your return now, we can just put it to 0 for now. Okay. So let's see how our trajectory looks like. We can just do a break. For only one trajectory. Now we have a trajectory. This is my trajectory. This is how it looks. Okay. Now return. For return, what I can do, I can just start from the ending, right? Start from the ending and do something like this. So let me show the recursion for return, how we can compute it. So let's say I have a trajectory S0, R0, S1, R1, S2, R2, dot, 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 ST, or ST minus 1, R, or let's not do it for a general purpose thing. Let's do it for only 4 transactions. S3, R3, right? I want to compute return for G0, G1, G2, G3. So G0 is what? G0 is R0 plus, let's ignore gamma for now. Let's just sum it. Let's assume gamma equal to 1. Okay. R0, R1 plus R2 plus R3. Then let's say transition to an ST next. This is the terminal state. Okay. Now what is G1? G1 is R1 plus R2 plus R3. That is G3. G2. G2 is R2 plus R3. And what is G1, G3? R3 only, right? Now see, a recursive pattern occurs, right? So let's assume this is the terminal state, right? G3. This one. Now this can be written as R2 plus G3. This can be written as R1 plus G2. And this can be written as R0 plus G1. Right? So if I just compute from the previous to the first, that would be easier. I can basically reuse the previous return, right? So that's what we will do. So exactly this will do. We'll just loop it from backwards. The last return is exactly same as the reward. Basically, we're doing an cumulative sum, right? A cumulative sum from the backwards. That's it. It's as simple as that. Now, if I just introduce gamma, that's a different factor. So gamma would be there. So gamma, if I introduce gamma, right? So how it will look? This is gamma, gamma square, gamma cube. This would be gamma, gamma square. This would be gamma, and this will be nothing, right? So you see, we just only multiply with gamma, everything falls into place. Okay, see, this part, if I just multiply it gamma, we get this entity. So gamma into G1 gives you this entire part. Okay. Now let's try implementing it. So for trajectory, what we need to do for transaction in, we need to go into reversed. So you get the last one that becomes my G, right? And my G initially is 0. G is equal to 0. Okay. So G would be G is equal to whatever transaction has the current reward, right? R plus gamma times G. That's the logic. So that's exactly what. So see, first time it will be the last reward, then current reward plus the gamma into last reward, then current reward plus gamma into last reward, last to last reward plus gamma into last reward. This is how the loop occurs, right? And after you compute this, you can just update it in the transaction dot G is equal to G. Okay. Why does it? Yes. So this is how you can compute G. So if I just run it, so you understand what it is going on, right? So you're just computing it from the reverse and then using that recursive structure to update the returns. Okay. If I run it, what it is, gamma is not defined anyway. Gamma equal to 0.9. If I run it, a G attribute cannot be set. So we cannot set it, but we can do a plus equals. Oh, it cannot be updated also. Name tuple cannot be updated. Wait. So this underscore replace thing is there. Let's see if that one works. Here underscore replace G equal to G. Yes. Now if I see the trajectory, it replaces, is it? No, right? Oh, sorry. Let's just not use then because we cannot update this value, right? Let's not use the transaction class then. We will use a data class or any class, let's say. Class TRANSSC transaction. It has init self a s a r s prime g s is equal to s. Just do it in a one line. A equal to a, r equal to r, s prime is equal to s prime, and g equal to g, and we'll do a self here, self dot, right? So you store everything here, and let's do a string method repr so that we can see it. Return if Same thing as this one, let's say. Self dot g, self dot s, s underscore self dot r, and that take these all thing we need to do because we cannot update the transaction class. Okay, self dot s. So now we have the same thing. We don't need the transaction class. We have a class for it. Okay, transaction 1 2 3 4 gives you same thing. Okay, now if I just do again thing and we do transaction dot g equal to g transaction dot g equal to 10, cannot set attribute. Why cannot I set attribute? Main transaction. Oh, oh, sorry. This needs to be transactions. Transactions. Now I can set attribute. Okay. Trajectory. Now you see we have computed all the returns. So the last state reached the goal state, right? So it has a return of 100, which is the last reward. Then it has gamma into the previous reward. Then gamma into previous reward plus previous reward, and all those things goes back to the first state. So initial states has minus reward because um, yeah, because it's so we can actually have gamma to be 1 just to verify once, right? See now it's something like this. See 100, then previous step has 99, then 98, 97 till you go back to all the way up to minus 312. Okay. Now if I put gamma to be 0.9, that gives me a forward loop of 10 steps only, right? So that's why my like returns become something like this. Okay. Now this one I can copy. After I am done with the entire trajectory, I can compute compute this, and then my data set is over here, right? Data is equal to an empty list, let's say. Or let's not have the data set. We already have the value and yeah, this value and n, right? We can we have the transaction over here. We have the return over here. What we can do, value transaction dot current state plus equal to return, and in transaction dot current state plus equal to 1. So by doing this, what we are trying to do, we are basically keep log of all the total reward, total return from that state, and total count of that state, right? Together during the G computation only. Okay. Now, after we've done with the entire data collection and stuff, what we can do, value would be your current value divided by n. That's it, right? You can then print the value, print p. And you see, we are basically summing all the return, right? So this is your total. Here it is your total value, so total return from a state. Okay, and this is your total count of that state. Now here I can actually, because I am looking for every visit or or first visit, right? Here I can put the logic. Here put the first visit logic. How? I can just maintain a visited set. Visited will be a state set if s or transaction dot s is in visited or not in visited, right? If it's a not in visited, then do this or skip, or just you do skip and put the state there, right? Mm, visited dot um, add, I think add visitor dot add your it can be a list also, not a set always. Append, then I can call append transaction dot s, and this is the logic for first visit. Got it? So if I run this, that gives me your Monte Carlo first visit policy evaluation. So let's just go over it once again. We have a world. There are 12 states. We get the v and n. Value is total value. Will eventually go to the value, and we can also write it as tv. Okay, so tv, and then at the end we use the v equal to tv divided by n. That also makes sense. So let's see. We have a random policy. We have a transaction class. We do interact in the environment for 10 episodes. We can have 100 such episodes. Okay. We compute the return for every such trajectory, update the total value and the number of visiting for first visit only. If we just comment this out, that would become my every visit. Okay, the visited logic. And then at the end, we close out of the environment, we get v is equal to total value divided by n. Run. Ended, right? It should not actually print, if there is any break, it should not print this step too much. Yes. So after all the trajectories that are run, we have this. So you see there is a nan value. Why? Because we have not visited that state. So the count of that state is 0. That's why we have an nan value. Okay. So we can increase the number of trials. See now if we can have that state visited at least one. Sorry. Still we didn't visit that state. So that may be some state where we don't actually visit it by interacting. Maybe another policy may be able to visit that state. Okay, let's see. Let's randomize the policy again. Run it again. No, that's some state in the environment which is not visited during this policy also. And what is that state? That's the last state, right? Oh yes, last state would not be visited, obviously. That's actually okay. So last state policy would be 0, right? So what we can do to stabilize this, actually
Sir, why
divide.
last state will not be visited?
It was last state will be like, so the update rule, right? So let's go here. Um, in this one, we are only caring about ST, not ST prime, right? Last state, S capital T would be, will not transition from there anymore, right? So the value for last state will be always 0 actually, right?
Sir, so we will reach the last state. Once we reach the last state, we will get a reward. For example, can you please scroll down here? R3 you have mentioned, right?
Yes. So this state, we don't get any reward further, right? So we are not getting, we are getting nan value for this state only, this state,
Correct, sir.
because we are not
Yeah.
transiting next from there. Okay. So what we can do to stabilize this is actually sum it. And why it is getting nan? Because the count is 0, right? We are not transiting from there. In it, like will not transit from the last stage, right? That's why it's becoming
According to
nan.
our
So what we
logic,
can,
sir, now
huh?
tr dot s. So it is having the last state also in count. Uh, when we
No.
reach the
Let's
terminal
let's
state.
S prime. So see, we are only tracking tr dot s, not the s prime. So after we reach the transition state at s prime, we don't transition anymore. Right? So after next state is the terminal state. We don't transition to the next, like next to next state, right? That's the last state. So it never put in this tr dot s. It's always in tr dot s prime.
Sir,
Okay.
but how that reward will be then captured?
No,
So in
there
our
is no reward.
trajectory, in
There
the
is no,
trajectory list,
see, there is no reward, right? There is no reward after this. So this last state, we are not visiting it from anywhere from there. There's the
yes, sir.
last
Well,
state.
just wondering how we will reward in our calculation will be captured in the when we touch that state, we will get the reward of 100.
No, we'll
And
get
that
the
will be
reward before transitioning to the state, right? Here. So here we will get 100.
okay.
Okay. So after we reach this state, we don't transition anywhere. So that state is actually never visited. After we go there, the environment just terminates. Okay. So what we can do to kind of stabilize this is actually put a 1 e to the power minus 7, a very small number with the this thing to not explode it to nan. So now if I run it, just to stabilize the division, that's it. Stabilize the division. Yes, now it's 0. Now it makes sense, right? The last state should see, in theoretically what is happening, value is how much return you are getting from that state, right? So from last state we don't get any reward. That's the last state, right? You get my point, right? You don't get any reward from that last state anymore. So so in that here, that last state, there is no RT, there is no RT over here, right? If there is an RT, then its reward the value would be RT only, right? Because there is no RT, the value of this last state will be always be 0.
Okay, sir.
Okay. So that's how you just stabilize the division with a small number adding to n, and then you get your value function for first visit. Now for every visit, you just need to comment out this visited logic. That's it. Okay. Now, what is the problem with this method? You have to wait for the entire data to be collected. Then you can evaluate the value, right? So basically it's the calculation is very much delayed. So you get hold of the value function after you have exhausted the entire or have collected a huge amount of data. So and this is called an offline. So why offline? Because during the interaction, you don't have access to the value function. You have access to the value function after you have done interacting in the environment. Okay. Now online method. So yeah, in the Monte Carlo online method, what we do, there is a very simple hack. So value is actually what? Value is equal to, currently it is total value divided by total number of visits of a state. Right? This is the thing. And now total value of S is actually what? Total value of S plus return of that state, and then n of S is equal to n of S plus 1. This is the thing that we are doing, right? What we can do, we can actually, instead of doing this at the end, sorry, let me just do at the end, we can maintain a running sum, or not a running sum, not it's a running average actually. Okay, so assume that we have a value function v. Okay, V of S. Okay. Now, if I want to update, let's say I observe a return GT. Okay, GS of a state, GS of a state. So that means I also visited that state, right? So n should be also increased. So assuming that I have an initial value of that state Vs, how I can update its value? So let's say I have visited that state for ns number of times, and that's my estimate for value is Vs. So what is the now I visited it for one more time and get a return of GS. So what is my updated value function? If I do a running average, what is my total value currently observed? V of S times N of S, right? Now, what is the extra value I got? G of S, that's my total now. And what is the total count now? N of S plus 1. That's my V of S, updated V of S. You get the logic, right? So this is my previous estimate. We observe it for ns number of times. So we just multiply it, get the total value, then update, like sum the current return and update, like divide it with the updated ns. And then we update the ns also. Ns is equal to ns plus 1 for the next time. So if I don't do this total thing and then divide it at the end, if I do this, then I have to only wait for one trajectory, not the entire 1,000 trajectories, right? Only one trajectory, I get hold of all the GSS, right? I can just update value for all the states, whatever state I have visited in that environment, in that trajectory. So if I just do some kind of optimization, uh, we can write it as so this ns can be written as Vs, ns can be written as ns plus 1 minus 1, right? Divided by, sorry, plus G of S divided by ns plus 1. Now I can divide it out. So ns times ns plus 1 minus Vs plus Gs divided by ns plus 1. Again, I can just open it out. So Vs plus Gs minus Vs divided by ns plus 1. So this ns plus 1, right? This can be like entirely the thing can be written as Vs is equal to Vs plus 1 divided by ns plus 1 times Gs minus Vs. That's the equation. And you do ns is equal to ns plus 1 after updating this. Okay. Or if you want to update it here, you can do the same. You can just update it before and then just do ns, right? That's, you're basically saving one addition computation. So not an issue. So by this, you can maintain a running average. So instead of collecting all the data, then doing the division, you can just collect the data for one iteration, right? And check, right? So let's do that. So it is more. So it has two benefit. One is you can check for optimality. You can check where VT minus VT minus 1 has a difference of let's say less than epsilon. So you can check for optimality, right? After each trajectory, you want to check for optimality. You can check for optimality when my value function is mostly converged, I can stop there. Earlier, it was not possible. Earlier, we need to collect a huge amount of data. Then we can, then if I want to check for optimality, I have to go again, collect a huge amount of data and check for optimality, right? And because the value was not updating, right? Last time we were basically replacing VT with the cut. So where is the, yeah, here, right? So it has nothing to do with the previous value function. So we cannot even check for optimality because we lose track of the previous value. But here we are actually updating the previous value from the current value itself. So we can check for optimality, one logic, like one advantage, and then advantage two would be uh, we have access to VP after each trajectory. So it's like if after each trajectory we have access to V. So we don't have to wait for an entire like data collection to complete, then we have access to V. Okay, so it's more responsive in a way. Okay, so let's implement this one. And it's the same logic occurs. So you can also implement the first visit and the every visit logic within this. Okay. So let's copy. Everything would be same. This is, let me just annotate this. This is Monte Carlo offline policy evaluation. Okay. Now we want to do Monte Carlo online policy evaluation. So why online? Because now we have access to the policy, the value of the policy in every trajectory, right? So you just copy the entire code as it is. In environment, we don't have to copy. Environment can be same. Policy can be same also for now. Transaction class is already there. We'll have this V and N initialized over here. We again go for the same 100,000 trajectories to update. And we are updating, we don't have to track TV. We can update from V only, right? Now state, we do this, we get interaction, we estimate every VS, right? Like GS. But here, instead of updating it for TV, what we can do, and we don't have to do this anymore, we can just do TVS is equal to VS plus 1 divided by NTRS plus 1. Just do another bracket. This is the 1 divided by NS plus 1, okay? Into, what was the code? GS minus VS, right? So G minus V of transaction of S. That's it. So with this, now every time we have a, like here, after every, like here we have a updated estimate of V. So I can print the V here, print V. Okay. Now we can also check whether it is converging or not, right? Now this is another advantage we have now. So here I can have values, right? And in values, I can append the L2 norm, right? NP dot linear L dot norm of V odd equal to 2. Now if I just print this, after we are let's say for 1,000 iterations, right, we can check whether it is converging to a right value or not. So let's see, and at the end we can always print v, right? So if I run this, okay, this is how we can we have to run this one first. Okay. Oh, PLT is not imported. Okay. And you see, so this is due to, see, this basically stabilizes, right? So basically you start with a lower value and then you just oscillate a bit and then you stabilizes. This is the behavior you observe in a model free method. So basically your value stabilizes after some, and it kind of reaches to an like the value it is supposed to be. So v. Okay. And this is your this is for your first visit, right? You have that visited logic again. Now if I just comment that visited logic, it becomes your every visit. Okay, you got the, like, what is the improvement, right? You now have access to value for every trajectory, and you can also check for optimality. Okay. Okay, now with this, can you tell me a way to solve the environment with this knowledge only? Anyone? So you can unmute and tell. So I can estimate the value of a policy by interacting in the environment. I don't have access to P and R matrix. I can still evaluate the policy by interacting in the environment with that policy. So can I solve the environment with this knowledge?
Sir, just one small doubt before this question, sir. In the plot, what you have done, what I'm seeing is like one value get going high and settling down. We have totally
No,
values for 10 different states, right?
no. We are actually in the norm of that value vector. It's the norm, not the
Mean value.
one value.
Okay.
It's the norm. So we are, for the 12 state vector, we are getting that your L2 norm, basically your x square plus y square plus z square root over of that of for all the states, and that we are plotting.
Okay, sir, got it.
Okay. So with this logic, and that gets stabilized, right? So basically all the values get stabilized. If the norm gets stabilized, means all the vector components also stabilize, right?
Yes, sir, got it.
So yeah. So with this logic, with this current knowledge, can I solve an environment? So we have covered evaluation, Monte Carlo offline, Monte Carlo online. Can we solve an environment with this knowledge? Solve an environment means find the optimal policy.
Based on value, we can, as the value updates, just like how we did earlier, if we get to know the value, then accordingly take action. Max of the
No,
for a
not
given
the max.
state.
Not the max. We cannot improve the policy from value, right? From value, we cannot improve the policy. So what we can do, we can we can get all the possible policies in the environment and then sort the policies based on the value,
Okay.
right? So let's
So
say,
last time what we did is we got the the earlier boot last time the date
this one.
earlier we did one algorithm, right, sir?
Yeah, this algorithm,
Uh,
right? But it has the Q function, not the value. It also have the Q function. Q function can give me policy. Like taking argmax, I can have a policy. But we are not computing Q function. We are computing V function for now, right? It's actually similar to your this case that we come up with all possible policies in the environment, solve them individually one by one, then rank them with the norm of the value. Then
yes.
whichever policy has the maximum value none, that is the best policy.
Yes, I got it. Yes.
Right? Yes. So with that the problem still persists. Now even my environment grows to three more states, it becomes four times four more computation, right? So still with we can solve a small environment with this knowledge with evaluation, but we cannot scale it. We cannot scale it for larger environment because my number of policies would be exponentially growing. Okay. So you see
Yes.
this model based, model free, all these are related. So now we are basically looking into how to estimate the value function from interaction rather than like bootstrapping or doing a dynamic programming on the P value and R matrix, right? So because we have P and R matrix earlier, we can do a bootstrapping and then get the value function by just running this loop, right? V is equal to R plus gamma PV, or by directly computing I minus gamma P inverse R. But this is not now possible. We don't have access to P and R for this case also, and for this case we need the access to P and R, right? But now we can do the same thing, but we can basically interact in the environment with that policy and get the value function. Okay,
Yeah.
and we can actually cross check. We can actually cross check. Wait, let me cross check. So we have a value function like this, right? And because we are using read world, we have access to PNR. So let's check whether the current policy have like what is the exact value function for the current policy analytic approach. Five. Yes, it has some norm also. So the norm we also print. So this is our estimated value function at its norm, right? And this is my actual value function and norm. You see, it's little bit bigger. That's okay, but that's mostly because of the last thing. This one. If you just ignore this one, and for the exact value function, this is sometimes it has to be zero. Actually, it's wrong because for a dynamic programming, you can only loop in that state, right? But for an interaction, you cannot loop in that state. So if I just put value, oh wait, v pi, and then do v pi last state to be zero. Yes, see how close we are. So with this method, with interaction method, we are at 93. With this method, with the exact method, where we need to know everything about the world, we are at 99. And see we can actually compare it, right? So instead of 95, we have 93. Instead of 9.8, we have how much? 31 or something. Oh, wait. So this is minus 8.31 minus 9 point something. And so you can basically see. So we can, for the non, we can directly compare both of them, right? They're very similar. There may be some positional disagreements. So some state might be visited less number of times, so their value gets less updated. With more data, will be more closer. But anyway, so you can see that if I know everything about the environment, my non comes at 99. Whereas if I don't know anything about the environment, I can interact infinitely in the environment. I came to 93. So which is like a pretty close estimate of the actual value. Okay. Okay. So this is
The
how we
gamma
can.
is same. Did we are our gamma is also 0.9.
Yes, gamma is also 0.9 in this case, I guess. Yeah, 0.9.
Okay.
Okay, so we learned how to do the same stuff until here, right? Now there is another method which is a much faster method that is
Sir,
called TT.
sir, sorry for interrupting once again. Sir, if I just I have pinged you in chat one image. If you see
Okay.
that It is from Sutton and Bartow book. There it is like the state
Yes.
ST plus one or RT plus one are together.
Yes, but in the
So,
last state, ST plus one, RT plus one is together, right? But for the last state, you don't get RT plus one anymore. For the last state, the last terminal state, RT plus one is basically zero. You don't get any
so
reward.
here, as per this diagram, if we see, we give a action decision from the agent. It goes
Mhm.
into the environment. The environment gives state and reward as outcome, right?
Yes.
So
Yes.
that way, then when we know the state, the terminal state, then only we will get the reward also, right? The terminal reward.
No, the
ST
terminal
is the
reward
final.
is the terminal reward is actually zero. So for the grid world environment, after you, so it's actually like this. The interaction loop looks something like this. So you are at S0, right? You don't get any reward for being in a state, right? Do you get any reward for being in a state? You don't get any reward, right? So you take action A0, you get a reward R0, and you transition to next state S1. Then you take an action A1, you get a reward R1, you transition to a next state S2. This is how it goes actually. Okay. Dot dot dot. You are in a
Yes,
state
yeah,
ST
I
minus one.
understood, sir. I think some terminology difference is that if we see here, the R0 is coming at S0 A0,
Hmm.
but ideally, according to the diagram, there should not be any R0. There should be only R1.
This one, right? Yes, yes. Yeah, that thing can happen. That small type of kind of terminological problems are there, but you get the point, right? This is the interaction loop. Okay.
Yes, sir. Now the thing is like our earlier method where we got the value for the terminal state in your matrix.
Mhm.
The other calculation we did, right, where we know the transition matrix and the reward matrix. Then we
Mhm.
have mathematically calculated. There we have value for the terminal state.
Yes, because you can kind of keep looping in that state. So there is no way to tell the dynamic programming algorithm that that's the terminal state. It can keep looping in that state actually. But for an interaction method, you cannot loop in that state, right? The environment will terminate by sending you that done equal to true. So that's why your value would be always zero for the terminal state.
Okay, okay, okay.
Okay, but for a dynamic programming algorithm, even if after you reach the terminal state, there is no way to tell the environment that that's a terminal state. It might keeps on looping in that state.
Okay,
Got it? Okay.
okay, okay.
That's why we
So
have a value for
that
the
one is
terminal state also.
it is 900 because it has done 9 times, sorry, 10 times and then 0.9 gamma.
Yes. Yes.
Oh,
Exactly.
okay.
Exactly. So okay. So now we learned how to evaluate a policy with Monte Carlo sampling. Uh, Another approach, which is a much kind of advanced approach, is TD learning. And TD learning, so till now, you see, we don't use or we don't exploit the Markov property, right? But we can actually exploit it. We can exploit it like this. Okay. See this equation. So TD learning comes from this averaging thing. Okay. So here the problem was we need to wait till the trajectory end. Earlier, we need to wait till the entire data collection end, right? Now we are much faster. We need to only wait till the trajectory end. But that also gives me some kind of responsive latency, right? We can improve it further. How? By exploiting the Markov property. What is GT? GS is what? R R plus gamma V of S prime. That's my GS, right? That's my GS. So we just substitute GS with an estimate of this. That's the TD learning. So now we don't have to wait till the entire trajectory. We can just substitute GS with its Markov substitute, like this Markov as approximation, right? That is basically R plus gamma of the next value, right? And just the equation becomes like this: V of S is equal to V of S plus 1 divided by NS plus 1. This entity, this GS entity would be transcend to R plus gamma V of S prime minus B of S. And this is known as TD estimate. Okay, a temporal different estimate, which basically harnesses the Markov assumption. Markov assumption, right? That these are all Markov machines. So we can estimate the current return to be return reward plus gamma of the next estimate return. So this is basically your estimate of G of S prime, right? So these two will be kind of covariate. So you just put this entire recursion instead of GS. So we don't have to compute GS anymore. We can just use the same value estimate we have for the next state and just do a bootstrap there. And to further simplify this NS, right? This component is replaced with a learning rate alpha. So, so see this NS, how it grows. It's basically 1 over T, right? So as time goes on, it basically converts to very small value, right? So, and it's actually very quick. So this downfall of this quantity is actually very quick, 1 over T, right? So after some time, it will be essentially very close to zero. So to kind of capture that in kind of in most cases, it's very close to zero. So rather than computing it and kind of updating the NS for the next time, you just replace this entire logic with a learning rate alpha. Alpha can be kind of an exponentially decaying thing, or it can be a constant, anything. Mostly it's a constant, let's say 0.001, which is approximately true for this entire half, where the value, where this 1 over T computation is kind of converging, right? So the TD learning equation becomes this: Vs is equal to Vs plus alpha R plus gamma V of S prime minus Vs. That's it. And you don't have to track how many times you visit a state or anything. You don't have to track anything. So you just, what are the things we are waiting for here? We are just waiting for S, R, and S prime. A, we are anyway getting it from the policy, right? So that means we have to only wait for a transaction to happen to update my value. It's actually much faster, right? We don't have to again uh, much faster, not faster, faster, right? So what was the logic? For Monte Carlo offline, we have to wait for the entire data collection. For Monte Carlo online, we have to wait for the trajectory to end, trajectory. And for TD, we have to only wait for S, R, S prime transactions. And they came from each other, you see? It's a incremental thing. So with this, now you don't have to even track how many times you are visiting a state. Every visit, first visit logic disappears. You just put everything for a learning rate and just keep interacting and updating the value. Keep interacting, updating the value. So you always have a running estimate of value that you are updating. Got it? So let's implement it. And this TD learning becomes the basis for all the next like value-based algorithms like Q learning, double Q learning, SARSA. All these algorithms came from this TD learning concept. And now you have a clear understanding how it came from, right? So we first compute the thing from a like total collect every return we are getting and then divide it with by n of s. Then we do a running average and then we kind of use that Markov assumption logic to estimate the g of s instead of sampling it or computing it for the trajectory, and then just replace the number of count with the learning rate because it will eventually, because it's a 1 over t trajectory, like t equation, right? It will eventually moves very close to 0. So rather than computing it, we can just put it as a learning rate. Okay, so let's implement it. uh, Same equation, same everything. Now we only need, we don't need ns now, we need alpha 0.001, possibly 0.0001. So it will be same as after you reach every state. 001 means after you reach every state for 1,000 times, it's basically learning in that rate. So yeah, this is called TD learning. We have the same values is fine. We are again interacting with 1,000 episodes for every trajectory. We don't have to compute all this thing now. We can update the value after we basically, we don't have to append it anymore. We just update the value over here, right? So value of, we don't have to even append it, right? So transaction TRANS transaction is equal to transaction of this. We don't need to track the trajectory. Value of transaction dot s is equal to value of transaction dot s plus alpha times what? R plus R becomes transaction dot r plus gamma times value of transaction dot s prime minus value of transaction dot s. That becomes my thing, and I don't need to update the count of the variable, right? Because we are basically replacing with a learning rate, and then we update the next state. We don't have to compute return or anything like this. Uh, yeah, after every trajectory ends, like we can update it after we are updating value function, but because just for computational efficiency, we can update the linear algorithm or the norm of the value after each trajectory ends, just to track whether it is converging or not. And we can interact it for, let's say, 100 iterations, 1,000 episodes, sorry. Let's run it. Let's see. 0, run. Still running. Okay. So my value comes here. Let's do the non np dot linear l dot non or equal to 2. It's at 31. So that means we need to interact more. Okay. So we need to interact more, but let's see how my value function converge. PLT dot plot values, and this is how we are converging. It's a much stable thing, right? It's a much stable, much this thing. So let's run it. Let's run it for more amount of time. Let's run it for 1,000, 10,000 steps possibly. You see how we are improving it, right? Earlier it was like, because we are updating at every trajectory level, it was very transient. Because now we are updating at every state level, it's more smooth. Okay. It's running. You have to wait for some time. And we have to basically see whether it reaches this analytic value or not. If it is reaching the analytic value, we are good to go with this algorithm, right? 5,000 episodes. And if I just render, right, you will see that it's actually taking action in that environment. It's just going moving left and right, either reaching to the final state or somewhere, and trying to get the rewards from there. So it's actually interacting in the environment. Because we are not rendering, you cannot see it. We are done. Okay, so what is the ordinal value? It's 36, but let's see. Yes, we are mostly converged. So what does it mean having 36 as the value? The learning rate is the thing. So if the learning rate is very small, um, so actually, as we keep track of the actual count, um, with more number of interaction, the learning rate, because it's actually going very close to zero, my updates become very small. Okay. Now, because we are having a fixed learning rate, my update becomes at fixed at some point. So after 1,000 visits of a state, my updates become fixed. So that's why um, it actually converts in a lower value, but you can compare the states. So if I see this v pi and v, right, we can check v pi and v. We can still compare which states are good or bad. See, this state is good. For this one also, this state is good, right? Uh, yeah, you kind of get the point. So because it's not exactly same as the v pi, but it also converges to some value. Okay, and with this you can also compare the policies. Okay, yeah. So anyway, so these are methods to evaluate a policy by interacting. We don't have any method to still improve on a policy. Okay, so that comes under the control part. If I just go over here, we covered this entire subtree. Okay, so evaluation, Monte Carlo offline, Monte Carlo online, and TD. Now there is a way, because we can estimate value, right? We can also estimate values, like state action value, that we can do just by taking, instead of only tracking S, we can track S and A occurring together, by which we can just also estimate Q values. But from Q values, there is a way you can extract a policy uh, with epsilon greedy sampling or Boltzmann sampling. Why greedy doesn't work, that's a separate case. That is the concept of, we'll not cover it today, but I'm giving one heads up that because we are interacting in the environment, acting greedily might not explore the different parts of the environment. So there is a dilemma called exploration dilemma, where you always want to explore the world first before exploiting. So your Q values or your values will be only good if you have a good understanding or good sample from the world. Now, because initially we have a random policy or a policy which is very, uh, let's say, conservative, right? Uh, if we update with that policy only, it gives me a bias estimate of value and Q. Why? Because it might not visit most part of the environment. It might not visit some part of the environment, right? It might take only left at some corner and not take the right. So we not see the entire part of the environment where we take right. So in those scenarios, we initial learning phase, we use a high exploration. So when the policy is mostly a random policy, you don't fix any action for a state. You just explore randomly for some time. As you learn, as you update your value function, you basically reduce your exploration and start exploiting. So that's your exploration dilemma. So why dilemma? Because there is no so there is all kind of proofs and all, but the dilemma is when to stop exploring and start exploiting. So there is a proof of this logic greedy in the limit of infinite exploration. So if I act greedily after exploring the environment infinite time, that gives me the optimal policy. But we cannot explore the environment infinite amount of time, right? So there is always this trade-off. When should I stop exploring? When should I start exploiting? Okay, so there are different heuristics or empirical methods we'll discuss. But yeah, you currently know how to interact in an environment and find the value of a policy. Similarly, you just replace value with q values, q and track s and a together, occurrence of s and a together. That gives you a q table, and the same algorithms apply. Monte Carlo every visit, so Monte Carlo offline, Monte Carlo online, and TD. All these things work for that also. But because you have a q value now, you can then improve the policy. That will do next. So in the next week, we'll see how to improve the policy. Let's say I have a random policy. I estimate instead of value, I estimate the q value of the policy with the same logic. Just track s and a together. Okay. Um, then there is a way. There are actually multiple ways. You can either do greedy sampling from the policy to the greedy sampling of the q function to get a policy. You can do epsilon greedy. You can do Boltzmann sampling. All of those things give you a policy from the queue. And if you explore the policy, like if you have a, this epsilon means exploration, how much you want to explore. Okay. And if you can control the exploration correctly, you can have a, like statistically, you can have an improved policy over the previous policy. Okay. Those comes under the control part of the algorithm. So control Monte Carlo offline, Monte Carlo online, same thing. You estimate Q and update the policy with epsilon greedy. SARSA is basically the TD learning thing, and Q learning is more or less like SARSA, but a little bit of twist is there. That's it. Then you are done with the model-free reinforcement. But this part, I guess, we'll do it next week. Okay. Currently, I think you appreciate the fact that we can evaluate a policy given given that I can interact in the environment. And with this, I can solve at least small environments where there are number of policies are very small, number of possible policies are very small, like 2-3 states environment up to 9 state environment. The number of policies are very small. So I can iteratively evaluate them and solve them. Next week, we try to move it towards improving the policy. Let's say I have a initial policy pi I. In the pi I plus 1, I will have an improved policy over I. So that I don't have to exploit, I don't have to go and brute force for every policy. I can improve on the previous policy, like statistically. Okay. So yeah, that's called. So what we covered is all these algorithms, right? And also give you an introduction to also give an introduction to control. What is this exploitation dilemma? And this thing will cover in more detail for the next week. Okay, and it will be much interesting to see. Okay, so any questions till now? And also, like, give me feedback how you like the sessions, whether you want me to like which parts you want me to focus more and all those things. Okay. And by the way, the question answering, right? Uh, I think we covered till week 1 to week 3. In the next week, we also cover from week 4, week 5, because those question answers are out. So we'll cover those 2 weeks. in the coming week.
Sir, yes, sir. I have one doubt, sir. Here,
Yeah.
this TD is having very low value compared to the other
Mhm.
methods,
Mhm.
right, sir? So, how can we bridge, sir? This means, if this sounds like through Monte Carlo, we are feeling a better value for a state
No,
compared to TD.
no, it's actually, it's not a better value. It's a, there is a bias actually. You can still compare the states as like the states which are good in your Monte Carlo is also good in TD, but there is a bias. So you basically assume that there is a fixed -50 with the Monte Carlo gives you TD, something like this. So you can still compare. So the idea is to whether you can compare two policies, right? Whether you can compare policy one with policy two, that still exists.
Policy
Okay, because
one. Okay, you are saying that policy one performance with TD evaluation will be equal, means it will be comparable to
yes,
TD evaluation of policy two. Okay, okay.
exactly, exactly.
But
So
yeah, value is a mathematical. Can we think of value as a like some mathematical fixed number for a given policy?
yes, yes. But this TD is actually a biased estimate. So biased estimate means there is always, so why it is a biased estimate is because we are bootstrapping on the same like erroneous value, right? So this is not a correct value. Initially, like earlier, we had the GT here, right? GT is sampled from the environment. So it was an unbiased estimate of how much return you will get. But this is, you see, it's a biased estimate. It's a bias. It's actually estimating from its own self, right? So that's why TD is a biased estimate, but the bias is consistent. So you get a, let's say there is a 50 bias, right? A negative 50 bias. So for the policy one, you will get a negative 50 with the original value. For the second policy, you will also get a negative 50 for the from the original value. So still you can compare both of them, but it will be off by some fixed value from the original value.
Sir, why are we calling this as a biased estimate, sir? I
Ye-
understand that the initial value of V S dash is not right and it eventually becomes better over time. But
Yes.
since we are running at 1,000 iteration of the 1,000 episodes, it
Hmm.
should gradually become
Yes, it should, but the error also propagates, right? So the error also keeps on propagating through the thing. So this is not actually sampled from the environment, right? This is actually estimated from its original erroneous like V estimate only. So it gives me a value which is biased with respect to the original value. So it's actually, see, it's converging, right? But it's converging at a lower value than the original value. But still you can compare between states or compare between policies. So basically, what I'm saying, same as the every visit thing, every visit first visit thing. So if you visit every time, you get a biased estimate. If you visit one time, you get an unbiased estimate. See, this is the first visit thing, right? Every visit can be more or less than the original value. It's exactly same. So because we are updating it from its own estimate, this bootstrapping it, RDD, this temporal difference estimate is actually a biased estimate of return. That's why the value function is also biased. And it's a consistent bias. So for policy one and policy two, you get a same bias. So you still can compare the policies, policy one, policy two, policy three, all of them they can be compared. Okay,
okay.
so you get the point, right? So it's basically some off than the original value. For us, it's like 99 minus 36, like around 50 something bias.
Yeah.
Okay. And you can see the same behavior if I do. So we already do first visit, right? If I do the every visit, you will see a bias. So it will be like instead of 93, it will be like 120 or something. So you have a 20 bias. But it will, that bias will be consistent across all the policies.
Okay.
Okay. Okay, that's the logic. So estimating value with interaction doesn't mean you reach to the optimal value. you reach to a comparable value across policies.
Got it. Got it. Yeah.
Okay, then I think we covered a lot. So I would strongly suggest you practice this. Wait, yes, practice this. Let me know if you face any difficulty. Okay, next day, I guess we'll start with control and finish up our model free interaction and also see the question answers for week 5. I think the sessions are helping you in your assignment solutions and stuff, right? And at least in theory and how it is implemented in practical code. Yeah, give me feedback so that I can tailor my uh, sessions that way.
Yes, sir, sure, sir. Yeah, I am today we have covered good amount of things, and we are able to really see how exactly the transition of different algorithms has come.
Yes.
It is
Yes,
very nice
exactly.
to see all of that in one go, and it makes a lot of sense now, sir.
Okay, 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 okay. Then let's see. We can cover next day. I guess the entire model free will be done. Then we'll go for deep reinforcement. And deep reinforcement actually borrows so much concept from these algorithms. We just have the neural network in that case. That's it. The algorithms are exactly same. So it will be very easy for you to understand how DQN works and all those things. Okay.
Okay.
Okay. Then I'm stop recording. Stop recording.